Okay, so now we learned several works and different works and energies. So let's uh, point out some common feature of all these things. First, uh, energy is the fundamental quantity to characterize the stage of the system. Okay, and work is the energy change associated with a particular process. So here, what I would like to emphasize that energy is related to the state, like the initial state and the final state. And work is related to the process. Okay, they're different. So basically, you can see at a particular point. Like say, if I'm standing here, I have some particular amount of energy. Okay, that's okay, is to say. But I cannot say I have some work when I'm standing here. Okay, work is just saying when a particular process, I'm doing some work. So at different process, you may have different work. That's something quite important. Or even graphically, you can think about. If you have initial point here, final point here, you can define the energy and here. Like say, you can say kinetic energy and the final point, potential energy and the final point. You can say the kinetic energy and the initial point, potential energy and the initial point, K initial, U initial. But we never call W initial or W final. We never say this stuff. Work is related to process. We can say the work for the process 1. We can say the work for the process 2. Okay. And we can see the work for the process like this. And of course, the work done by the conservative force is independent with the path. So if the force is the conservative force, you evaluate it with different paths, you get the same value. So in that case, we actually can introduce a potential energy. So we don't have to talk about conservative force because it's actually independent with paths. So we can relate it, we can introduce a potential energy and relate it to the state, initial state and final state. So the only force we have to worry about is non-conservative force, which is depend on the path. Okay? So hope you can try to think about the logic here. How can we deal with different terms, different forces? Okay? And by the way, for both of the energy and the work, the standard unit is J, okay, joule. 1 joule equals to 1 kilogram meter squared divided by second squared. Okay, you can check that. In any case, for all this definition, they have the same unit. 1/2 mv squared mg y 1/2 kx squared or f multiplied by x. Okay, kinetic energy, gravitational potential energy, spring potential energy, work done by a force. All of them, if you check the units, all of them can be written in this form. Okay. Now, we're going to talk about the conservation law of energy. Okay. It's always in the form like this. Some kind of change in energy equals to some kind of work. For example, we derived the work kinetic energy theorem. The change in the kinetic energy equals to the work done by the net force. Okay. If you try to calculate the other kind of energy change, it may be related to other kind of work. Delta K is related to the net work. Okay. So, in fact, all these energy conservation law, they are just modified from this work kinetic energy. Okay. You have only one law, in fact. conservation of energy, but they take different forms as they may be useful at different situations. So let's look at how can we get the different form of the energy conservation. Let's start with the work net energy theorem. Delta K equals to W net. Okay, we get it by integrate the Newton's second law. Now, the key issue is that we realize that the work done by the net force, you sum the work done by all the individual force. And of course, you can write it as two parts. The work done by all the non-conservative force, and the work done by all the conservative force, right? Okay? And we can define the potential energy change to replace the work done by the conservative force, right? So this is actually delta K equals to WNC. This is negative delta U minus delta U, okay? Now, this is some energy. Let's put the energy to the left-hand side. So we get delta K plus delta U equals to W and C. So the summation of kinetic energy change and the potential energy change equals to the work done by the non-conservative force. Okay. So this will give you another form of energy conservation. And here we can redefine this term. Delta K equals to K final minus K initial. Okay. Delta U equals to U final minus U initial. And if we rewrite it, we can get K final plus U final subtract K initial plus U initial. Okay. So it's good to define this K plus U as mechanical energy. So you get this is E initial. Okay. So we define the mechanical energy E equals to K plus U. Okay, that's the summation of kinetic energy and the potential energy. So that equation can also be written as E final minus E initial equals to WNC, or delta E equals to WNC. So that's another form, okay, for this one. Okay, they're actually the same equation. We just rewrite it in different way. So you can see here, if you try to calculate the change in the kinetic energy, it's related to the work done by the net force. If you try to calculate the change in the mechanical energy, it's related to the work done by the non-conservative force. Okay? Now, important issue about this equation is that once we write this into this equation, we can try to write it like this. Okay? Usually, when we can write a spatial case. So when W and C equals to 0, okay, if somehow we have this situation, then this equation becomes delta E equals to 0. Okay. So this is called mechanical energy conservation. Okay? So the mechanical energy conservation is actually a spatial case of the total energy conservation. This is called the total energy conservation. This is called the mechanical energy conservation. Okay. By using this definition, we can rewrite this equation back like delta E is, you can write it as different way, like delta K plus delta U equals to 0, right? Because delta E equals to delta K plus delta U. And you can also write it, this is actually K. Okay, this one is actually K final minus K initial plus U final minus U initial equals to 0. So K final plus U final, we move all the negative term to the right hand side, become positive. K initial plus U initial, okay? Or E final equals to E initial, okay? These two are also the mechanical energy conservation. Okay, you just rewrite that equation. So that says that, of course, this is in the more obvious statement. If the mechanical energy is conserved, of course, the initial mechanical energy has to be the same as the mechanical energy. And if you look at this equation, you can see the essence here of this equation is actually the mechanical energy contains two terms, okay, K and U. So you can somehow manage this equation in a way, if you increase U, you can decrease the K to satisfy this equation. Or if you decrease U, you can increase the K to satisfy this equation. Okay. From this one, you can see that the change in the two should compensate with each other to make 0, okay, for the total mechanical energy change. Okay? So, and by the way, if we use, usually we use subscript 0 not to denote the initial position, and without subscript, we mean the final position. So in that case, you can write this as K initial plus U initial equals to K plus U. Okay. This one is E naught plus equals to like that. Okay, it's just a notation. You can use different kind of notation. That's your choice. Okay. Now, since we have two situations actually, okay, this equation and this equation, and let's check when should we use mechanical energy conservation and when should we use the total energy conservation. Okay, so and this equation is actually equivalent to this one. So we don't only need to look at these two, okay? And the other boxed equation actually just some variant form of the two equations. Now, so we try to define the conservative system and non-conservative system. Please note that we already defined the conservative force and non-conservative force. And the conservative system and non-conservative system are more complicated. They are not directly related to the existence of the conservative force or non-conservative force. They are actually defined by the conservative work and non-conservative work. Okay. So the definition simply takes that. For the conservative system, the work done by the non-conservative force equals to 0. So WNC equals to 0. And the non-conservative system, so you have some work done by the non-conservative force. So WNC equals to non-zero quantity. So if you look at this equation, these two equations, that's very clear. What's the difference between the two equations? And right hand side, WNC equals to non-zero or 0. Okay. So that's why, okay, that's the work done by the non-conservative force is essential quantity to determine what system we are talking about. WNC, if you can try to find out the value for this quantity. If it's non-zero, it's called non-conservative system. We have to use this equation. If it equals to 0, it's called a conservative system. We have to use this equation. Okay? Any question here? Look at the quantity WNC. You always need to look at. That's our criteria. If this quantity equals to non-zero, if you somehow can evaluate it, okay, or I give it to you, or you can analyze the system to find out it. If you find that this is non-zero, then you have to use this equation, right? And we call this kind of system non-conservative system. If you find out the WNC equals to 0, then we have to use this equation. Or in fact, we better to use this equation. This is just special case of this. We call this kind of system conservative system. Okay. It's about the work done by the non-conservative form. WNC 0 or not. Okay. Basically, it says that WNC, if it's not 0, non-conservative system. The equation you are going to use is delta E equals to WNC. If WNC equals to 0, it's called a conservative system. You are going to use delta E equal to 0. So here, that's what I'm saying. The mechanical energy for the conservative system, mechanical energy is conserved. So delta E equals to 0. Okay, it's conserved means the change in the mechanical energy equals to 0. And for the non-conservative system, delta E equals to non-zero quantity. So it's not, mechanical energy is not conserved. Some of the mechanical energy will go to other form of the energy, but the total energy is still conserved. So in this case, it will be delta E is not 0. It equals to WNC. Okay? So if you look at some example for the conservative system, the most famous example, of course, will be the free falling in vacuum. Okay. In that case, the mechanical energy is conserved. You can try to calculate for any initial position or final position. You can try to calculate the summation of the kinetic energy and the potential energy. You will see that the summation of the kinetic energy and potential energy for any point along the motion will be the same. It's conserved. Okay. So when you drop it, the kinetic energy increases, but the potential energy decreases. Okay. The summation keeps the same. And for the non-conservative system, it happens whenever, okay, you have some frictional force. Like say, moving along a frictional surface, the mechanical energy will actually decrease because some of the energy mechanical energy will be changed to thermal energy by the frictional force. The frictional force, you know that it will, when you have frictional force, it will hit the object, okay, and makes the so extract the mechanical energy, transform it to the thermal energy. Okay. So they are the conservative system and non-conservative system. And here I would like to emphasize that conservative system and non-conservative system is defined in terms of the work, WNC, but not the force. So usually you cannot simply identify conservative system and non-conservative system by looking at the existence of non-conservative force. Okay. Let's look at some situation here. Please determine for the following system if they are conservative system, non-conservative system, or cannot be determined by the given information. Okay. So first, a system with conservative force only. Is this a conservative system and non-conservative system?
Conservative.
Conservative system, right? And can you justify it by looking at the work done by the non-conservative force? Is it zero?
Yes.
Because you don't even have non-conservative force. So of course, the work done by the non-conservative force has to be zero, right? But now, if a system has only non-conservative force, is it conservative system or non-conservative system? Non-conservative system? Are you sure? Or cannot be determined? It cannot be determined by just given information. Okay, yes, you have a non-conservative force. But even when you have the non-conservative force, you still have two possibilities. One is that this non-conservative force are doing some work. So you have non-conservative work equal to non-zero. So this is non-conservative system. But it's possible that you have a non-conservative force, but it's not doing work. This is still zero, right? This is possible. So in this case, it's still conservative system. Okay? Think about this. An object moving with okay. So let me think about this one. Okay. In a vacuum. So like some planet, okay, or some object moving, not planet, okay, some object in the vacuum with in a circular form, okay, with some tension. Okay. If in the vacuum without any gravity, any frictional force, you throw, okay, you are rotating some object with a tension. Tension is non-conservative force. So you have only non-conservative force tension, right? But in this case, if it's a circular motion, you see that the tension doesn't do any work. The work done by the tension equals to zero, right? How do you know the work done by the tension equals to zero?
Because it's perpendicular.
Okay, because if it's a circular motion, the force is perpendicular to the motion. And in that case, no matter how large the force is, the work is always there, right? So here you have non-conservative force, tension. But the work done by the non-conservative force is still zero. So this is a still conservative system. Because you can maintain a uniform circular motion, so the velocity doesn't even change. The speed doesn't even change, right? Okay, so delta E doesn't change. So please be careful. Okay, a system with both conservative force and non-conservative force, is it what kind of system? You have both conservative force and non-conservative force.
But you still don't know?
Cannot
For the same
determine.
reason.
Okay, similar to that one, right? For one non-conservative force, it can be conservative and non-conservative. If you add some conservative force, it still can be conservative or non-conservative. It's initially conservative and conservative force is still conservative. It's initially non-conservative and conservative force is still non-conservative, right? Okay? So please think about these different situations. Sometimes it can be quite tricky. So the three situations corresponding to conservative force, that can be both, this can be both. Okay? So can you give some example where you have non-conservative force but the system is still conserved? This is one case. You have only one non-conservative force, but the system is still conserved. There are more examples. If some object moving on a frictionless surface like that, you have a gravitational force. This is a conservative force. You have the normal force. This is a non-conservative force. force. Normal force is non-conservative force. But this is conservative system, right? You have non-conservative force, but it's conservative system. Okay, so anyway, the key information is that don't try to judge the conservative force and non-conservative force by looking at the existence of conservative force or non-conservative force. You have to look at the work done by the non-conservative force. Okay. Like this. You need to look at the work, not the force, because it's possible that you have the force, but the force doesn't do any work. Okay, so that's a non-conservative system. Let's stop.